I'm your host, Grayson Brulte. Welcome to another episode of SAE Tomorrow Today, a show about emerging technology and trends in mobility with leaders and innovators to make it all happen. On today's episode, we're absolutely honored to be joined by Tabor McCallum, founder and CTO of Space Perspective. On today's episode, we'll discuss the company's advancements in launching commercial balloons into space with Sir Richard Branson as the first co-pilot. We hope you enjoy this ride. Not the ride, just the episode. Tabor, welcome to the podcast.
Thank you.
It's great to have you here. Space is awesome. There's no other way to say it. And congratulations on having Sir Richard Branson join as an investor. And he'll also be the co-pilot for your first commercial flight. Why build Space Perspective now? You have a long background history in space, but why build it now?
Well, I think it's very clear that there is a market now for the space experience, that people think about it, fantasize about it, see movies about space, and that very unique perspective that going to space gives. And so then the barrier is the trip itself on a rocket and the cost of doing it. And so our market studies show very clearly that as you bring the cost down and the accessibility up, you really end up with an amazingly huge market for the experience.
Was the balloon approach taken because of the cost structure versus a rocket?
It's both. The balloon gives us a very gentle, slow ascent and descent, and it is a safety benefit, if not, in fact, certainly in perception. And of course, the cost side of it figures in as well. So it's a mix of all of those things. We go 12 miles an hour versus thousands of miles an hour.
So it's slow and steady as she goes then. So there's no turbulence, there's no bippity boppity, it's slow as she goes.
Pretty much. We're sort of bicycling speed to the edge of space. So it takes us a couple of hours to ascend from launch to 100,000 feet, which is just over 30 kilometers. We're there floating on top of the Earth's atmosphere, a little bit like an ice cube floats on water. Then after a couple of hours there at the edge of space, we descend back down, which takes a little over 2 hours to splash down.
Wow. So versus a rocket, so Sir Richard has Virgin Galactic and you're up there, I think, so let's say 10, 15 minutes. Your experience, you're actually up there a couple hours then.
You're at float for a couple of hours. The whole flight experience is 6 to 7 hours in that range. And so it's a much longer, gentler experience that gives you time to do things. And also the other side of that interesting market is creating a platform at the edge of space for events, music events, all kinds of interesting ideas come to us every day of things that people want to do at the edge of space in a large capsule.
So you're in the experience business then, essentially.
Absolutely. It is very much an experience business. We even have an experience team that thinks about the end-to-end experience that people will have, but it's very much an experience market. And what's interesting about the experience market, which is in essence the sort of tourism market, is that it's growing, that people are tending to want to buy experiences, especially experience with loved ones, over material things. And so we're seeing growth in that market as well. Yeah,
we are. When you look at data in the market, you're seeing the slowdown in the European luxury goods. We had a big report this morning that the slowdown in wine consumption. And you're right, a lot of that money is going to experiences. Experiences, I was very fortunate. I got to go in and ride and experience the Goodyear blimp, going up and down the Vegas Strip, and that was a lot of fun. But it took me a little while to get used to being in a balloon and getting comfortable. When an individual or individuals goes into your balloon, how do you get them comfortable over that initial, wait a second, there's no wings here? Because some individuals get a little concerned about that.
I think that's largely being worked through in how we design the interior of the capsule. It's sort of one thing if it's, stark and you have, seats next to windows. We think of this more as a space lounge. We arrange the seating in a way that it is as much a shared experience as it is an experience looking out the window. There's a bar and a lavatory and places to stand and walk around. So and actually even plants, by making it a sort of familiar, comfortable environment, you take a lot of those, what we would say are blockers to the experience away. We've had a lot of people who say they weren't, they were sort of nervous about going, didn't really want to go, but then when they saw the interior design, they're like, yeah, I could do that. That's really that's something I could go do. So it's inviting in a way that sort of your classic capsule interior design is not.
You have a bar in space, the world's highest bar. It becomes part of that experience there.
No real ship doesn't have a bar.
Absolutely. So you had the experience down from a technical perspective. How did you achieve it? Did you have to build something new? Did you have to invent something? How did you get this to create this cocoon, warm environment from a technical perspective?
Well, it's a mix of existing technology and putting together novel combinations of current technology. So the balloon itself goes back to, you first see these kinds of balloons in the late 50s, early 60s. NASA's been using them for science for decades. So the balloon itself, while we have made a lot of improvements in its strength and manufacturing control, is existing technology. We've put capsules in space before. This one has some sort of special thermal heat rejection requirements because we have 9 people in such big windows. And, we have used ships before, but what we really put together was how you take one of these balloons that go to the edge of space with the largest space capsule ever made and launch it from a ship and splash down in the ocean. It's that combination that really was the challenge getting through the test flight that we did a couple of months ago.
Why launch from a ship? Obviously, you're going to land in the water, but is there any something that's unlocked by launching from a ship?
2 things are unlocked from launching the ship, principally. One is scalability. Scaling around the planet, it's much harder to get launch sites on land, get all the permissions, work through all the safety issues of launching from land, versus launching from the ocean. I don't have to go through all of those exercises in order to scale operations around the planet. The other thing that the ship gives us is a much wider range of environments that we can launch a balloon in. As you can imagine, launching a 550-foot tall balloon is somewhat sensitive to the wind. And what a ship does is control the direction of that wind, by which direction we point the ship, which is a huge benefit, and then can control the speed of that wind simply by canceling out a lot of that wind through the speed of the ship through the water. So we're able to create ideal launch conditions out of what would otherwise be untenable launch conditions for the balloon. So it increases our operations cadence and allows us to scale around the world.
It's clearly a lot of advantages there. Was the ship always your primary focus for launching the capsule, or did that come after an immense amount of research and due diligence?
It came after a lot of resistance to that solution. As you can imagine, ships are both expensive and require work in a very large regulatory environment. And we looked a lot at launching from land, landing on land especially, and with a balloon system, the safety benefits of a marine launch, and especially a marine splashdown, are tremendous. If you try to come down under a balloon from the stratosphere and land on a spot, is virtually impossible. So you end up transitioning from a balloon to flying under a parafoil, and you see a lot of websites where people say that's what they're going to do. But then it turns out that transition from a high enough altitude to be useful is pretty dangerous, and then actually statistically being able to guarantee you will always get to a primary or backup landing site anywhere along the trajectory of the flight that day creates a further safety issue that we just couldn't get by all the safety issues of a land landing, especially. So once you've already bitten off that you're going to do a splashdown, because it's hard to miss the ocean, then doing a marine launch was the natural derivative of that, so that the entire operation is now mobile.
How do you pilot a balloon? Obviously, Sir Richard's going to be your co-pilot. Sir Richard's been around the world, I believe, several times. To a matter of fact, how do you pilot a balloon?
So, piloting a hot air balloon or a sport gas balloon is you have the ability to go up and down pretty much as you please and choose landing sites by controlling the buoyancy. When the balloon is going all the way to the edge of space and all the way back down, for a lot of reasons, where you really end up is needing to predict where that splashdown will occur. So we have extensive models that at any given time show if we were to launch from a given location, this is the direction that we would fly. So we control the landing site location along the axis of travel by simply when we begin the descent. And then the ship, the retrieval ship, takes out the other direction by going one way or another to meet the spacecraft at splashdown. So we're able to both predict where the splashdown will occur and adjust it sort of in real time through the course of the flight.
Oh, that's false. So when you're launching it, two ships then go out into the wild with you, one to launch and one to retrieve?
Yes, exactly.
What type of gas is it? Is it hydrogen? What type of gas is allowing your balloon to go to 100,000 feet?
Yes, we use hydrogen. We could use helium, and we looked at that pretty extensively. And when you really dig into the availability of helium and the already competitive market for helium, we found ourselves competing with hospitals for running MRIs. And so when we looked into hydrogen, it turns out that in the history of hydrogen ballooning, which is really extensive since it was the lift gas of choice for most of the world since the very beginning of ballooning, there hasn't been a balloon accident attributed to the use of hydrogen in the history of ballooning. So then, of course, everyone says, well, what about the Hindenburg? Well, the Hindenburg was actually designed for helium, not designed for hydrogen, and had a lot of flammability issues in the materials it was made of in the first place, and that was 80 years ago. So that really doesn't apply to a balloon application. So yes, we've adapted hydrogen and found that the growing hydrogen economy really supports what we're doing in our operations.
When you're at 100,000 feet, there's a lot of elements. It's cold, but there's a lot of elements. You have the heat issues. How do you space-proof a balloon? Did you have to use certain types of materials, coatings? What did you have to do to space-proof the balloon?
We go through a large amount of work to get the balloon materials to withstand the range of environments that it's in. The tropopause, which is where the troposphere that we're in meets the stratosphere, can be minus 80 degrees C, so it can get very cold. And then when we're at float at 100,000 feet, the air is extremely thin, so we're predominantly heated up by the sun shining on the balloon. So it's really been a materials challenge that has been addressed historically and worked out. And then we take those requirements and those techniques and then sort of bring them to a new level of safety.
What materials did you use? Were you able to use off-the-shelf materials, or did you have to use a combination of materials to ultimately achieve what you were able to achieve?
We use a type of polyethylene and did a lot of work to create a special type of polyethylene for our specific use, though historically polyethylene's been used by balloons that NASA and others have built now for decades.
Is there I don't know if this is the right term, a shelf life where you, based on tests, perhaps simulation, where you're expecting the balloon to last X amount of flights, or if you want to use the term, X amount of hours, and then you'll bring it back down and retire it and put a new balloon? Is there any shelf life on those?
Well, so the balloons are single use. When they're inflated, they're over 300 feet across. When we launch, they're 550 feet tall. So we don't reuse the balloon. So then we just have to rate the materials for, say, a day's flight time, which is relatively straightforward. So we don't have UV issues and the like, just since our flight time is relatively short and we don't reuse the balloon.
How about from a capsule perspective? Does that have a shelf life on the capsule?
Well, if you look at aircraft, say composite aircraft, you get tens of thousands of pressurization cycles, takeoff and landing cycles. So if we applied the same to the capsule, which has a a splashdown, which is sort of like a takeoff and landing cycle, and gets pressurized, much the way an aircraft gets pressurized. We think we're going to get the same number of uses from the capsule as one might expect to get from a composite aircraft. Even if you reduce that by a factor of 10, and we had thousands of uses, we're already at the point where the attributed cost of each flight to amortized across the capsule is so low that it's not a significant part of the overall cost of goods.
Very similar to a commercial airliner, then, where you just retrofit and redo the interiors over time, since the capsule itself will still be usable?
I'm sure we'll be reworking the interior. An interesting thing about the interior also is that we're keeping it flexible so that there are a variety of events we could do with the capsule inside. There's bands that want to play and things like that. So we have the interior flexible both to allow maintenance and the like, much the way an aircraft does, but also so that we can create different environments inside and support different kinds of events.
Since you're going to have a water landing, you're going to have a bar. I'm very proud of you for that one, because you can't have a ship without a bar. You're going to have bands. They're going to have instruments. What does it feel like when the capsule hits the water? Is it a noticeable impact that your passengers will experience? What will they experience when they're hitting the water on a splashdown?
So it's something we put a lot of work into. When you look at the capsule design, we have something on the bottom called a splash cone. And what that does is attenuate the splashdown by allowing us to essentially splash down with a point, and then also stabilize the capsule once it's floating in the water. So a splashdown will be a little bit like a hard aircraft landing. It's pretty short, and everybody will be in seats that really support them well. So I think as long as it's something everyone's waiting for, and we sort of say 3, 2, 1, splash, it's a fraction of a second event that at this point does not seem to be an issue for people as long as they're ready for it.
When you're developing the experience, the technology, the overall product, did you use simulation at all to run different scenarios when you were developing it?
We use a lot of simulation. We've actually, a lot of people use the term digital twin. We have sort of different parts of digital twin, but certainly thermal is a huge one for us. When we're at 100,000 feet, because we're moving with the air effectively, there's no convective heat transfer, so it's all radiative. And so a lot of thermal modeling went into that. And then, of course, as we're going through the tropopause where it's very cold, a whole other set of thermal modeling. We model our heat rejection system. It's an active system for getting rid of heat and radiating it away. Of course, the structure itself is extensively modeled, and we have hundreds of strain gauges that are used to monitor how the structure is behaving through different phases of the flight, temperature sensors and the like as well. So there's a lot of, sort of goes on in the modeling, from atmospheric management to just modeling how the splash cone works and how the balloon behaves and materials of the balloon behave. Modeling is an extensive aspect of getting this done.
If the simulation wasn't as advanced as it is today, would you be getting ready to do a commercial launch if you didn't have access to simulation?
No, I don't really think that a lot of current commercial space is viable without computing tools. It's really one of the big improvements in productivity that enables commercial space to occur. When we were building Biosphere 2, the personal computer came out, and there was a day in the middle of building where we took all of the drafting boards out and put in CAD stations, and the productivity shot up, as one would imagine. So just our ability to do the modeling in the first place and the productivity gains from simulation are really enabling.
In all of your modeling, have you identified a location in the oceans where it's an ideal launch point or something with a current that went historically where it says, okay, this is the most ideal place to launch space perspective? Have you identified that location?
Our surveys show there's a lot of locations, and the ships allow us to essentially craft a trajectory set for each of these locations. So not really an ideal place, but certainly many locations. There are some locations where seasonally it's not as good as other locations would be. And so part of what the ships also allow us to do is move our launch site and retrieval sites seasonally, say from the Northern Caribbean to the Gulf, for example.
There's a lot of opportunity in the fact that you're flexible, because I can even see a thing where you're in Antarctica, part of a cruise, and then they can add this as an add-on. Becomes very, very interesting there. When is Sir Richard going up to co-pilot? When are you planning to launch that mission?
We're still in planning, so I'm not going to give a hard date right now. We've been looking at end of next year, maybe into the following, but really it all revolves around getting through a series of testing gates that are done principally without people, or in this case, all without people, where we test things like the parachutes in case something happens with the balloon or the thermal control system. And so once we've accomplished those gates, then we'll be in a position to start human flight.
And then presumably after that, at a predetermined time, not going to ask you for a time, that you will launch commercial service to members of the public at some predetermined date in the future?
Yeah, so the licensing to do human flight, even under an experimental license, is very, very close to the licensing required for commercial flight. So I don't really see a big gap between our first few human test flights and going into commercial operation. I think once we've done flights without people sufficiently, we'll be just sort of looking at the details of human flight before we get into commercial operation.
I'm really curious. You mentioned the parachutes. How does that work from a safety perspective? Is that on sensors? Is it all automated? How does the parachutes know when to deploy?
So in a normal flight, we would never deploy the parachutes. And you're right that automation is a very key aspect of safety. So really, if something were to happen to the balloon, and we're sort of in this interesting predicament where we can't figure out what that thing may be, but let's just say, okay, something happened to the balloon, then our descent rates would be such that we would simply start, depending on where we were in the flight cycle, deploying the parachutes, and that would be an automated process or something that a crew member in the capsule could also do. So the key to safety in our case and in many cases is something called dissimilar redundancy. So the balloon can bring us back down to the water safely, and so can the parachutes, but they operate under very different principles and are completely separate systems. And so by being dissimilar, the same thing that caused the balloon to fail wouldn't cause the parachutes to fail, because they're different systems and wouldn't be subject to the same fault causes. So having parachutes as a backup through the entire flight and then being dissimilar to the balloon adds a level of safety that it's hard to match in any other system.
It builds confidence. Somebody like me, you got probably, okay, let's go try it. And to me, it's just it's a confidence booster. Are you seeing that with your prospective customers, where they know that you have a redundant safety system? Does that help build that comfort?
What we find is that it's a balloon and it's slow, and there isn't a huge explosion going on with a rocket, gives a sense of safety that rockets just don't inherently have. And then when we dig into sort of the redundancies and the way the parachute works and the like, that gives more confidence. So yeah, it gives us confidence in a system that we can use over and over and over again safely. Part of, I think, the real trick here is building a system that you can operate day after day after day, and it's safe. It's you can sort of do it, a one-off superhuman, do something like breaking an altitude record like we did with the Alan Eustace StratX jump. That's one thing, but a routine day in and day out operation requires a whole different level of the system, both in its development and training and of people and the crew and the like, but also in its inherent safety. You can't take something that's inherently unreliable and make it reliable through better operations. But you can take something that's inherently reliable and through great operations make a reliable service occur.
Absolutely. How many capsules are you initially planning to build and launch?
Well, we really don't have a sort of a cap on that number. So we'll have operating units that are, a launch and retrieval ship and 2 or 3 capsules, and then continue building those operating units and deploying them around the world. The market is so large that we don't see a time when we wouldn't continue to build out capability.
There's clearly a market there. Outside of space exploration, what other opportunities could you see being unlocked with Space Perspectives technology?
So there's the big market of just straight people having the experience, but we're also seeing, as I said, events. Is it the first poker game in space could be really interesting. Music releases, leadership podcasts. So the list sort of goes on and on. Obviously, things like weddings and the like. Because we have space and time, we're able to offer a pretty wide variety of different uses of the platform. And on top of that, there's a lot of interesting scientific uses where we carry instruments. Because we have a large number of flights, we're able to address questions in science that require a large number of measurements done around the year. So if we look at things like the rate that carbon dioxide or other greenhouse gases released at the Earth's surface migrate up into the stratosphere, you can measure that in many ways by monitoring those gases through the ascent and descent of the balloon and seeing how does that upwelling and mixing change through different parts of the year at different levels of the atmosphere, through the tropopause and the like. So there's a lot of very interesting atmospheric science questions that we can address simply because we're doing a large number of flights.
When you large number of flights, will that be, when you're fully operational, will that be multiple flights a day, or will there be a large number of flights over periods of days?
Fully operational around the world, it will be multiple flights a day. As we get started, we're going to start slow and ramp up to that and add capability. But certainly in full operation, you'll be seeing flights from around the world all the time.
Fantastic. You have a very bright future what you're building with Space Perspective. It's going to be interesting to see how your customers utilize your space. It's going to get very interesting, and I'm curious to see over time how the technology evolves as things get lighter and stronger. David, this has been a really insightful conversation. As we look to wrap up, what would you like our listeners to take away with them today?
I think that the main thing to take away is how technology development on top of healthy capital markets really allow new things to be brought to market, new scientific questions to be addressed, and new services to be given. So we're at a really fantastic time in history where we have incredible ability to model and simulate and design very rapidly, and a material base that's extraordinary. So really, I think these opportunity to do these kinds of things is relatively new. Just looking at battery technology and the weight reductions we get from current battery technology alone is enabling communication and navigation systems. There's a lot of areas where maybe even 5 years ago, this wouldn't be anywhere near as viable as it is now.
You said it beautifully. Healthy capital markets enable technology to scale. It allows innovators and entrepreneurs to build products that will go on to change the world. Today is tomorrow. Tomorrow is today. The future is Space Perspective. Tabor, thank you so much for coming on SAE Tomorrow Today.
Thank you.
Thank you for listening to SAE Tomorrow Today. Be sure to join us next week as we talk about maximizing ice efficiency in the new era of mobility.
SAE International makes no representations as to the accuracy of the information presented in this podcast. The information and opinions are for general information only. SAE International does not endorse, approve, recommend, or certify any information, product, process, service, or organization presented or mentioned in this podcast.